Okay, I hope my screen is visible for you. Okay, so today we will be discussing more about sun. Okay, so just a second. So as you know, the sun is the nearest star to our sun, Earth, and the nearest star to the solar system is Proxima Centauri, as you know. And its size, its shape, I will also include those things. Okay, I'm not explaining those factors like the weight and all. We will discuss that later while doing some problems related to or some calculation related to all this. Okay, so don't worry. Now the thing, let's see the composition of sun, and that composition of sun is something like this. So the hydrogen is actually that is here you can see this table in two-way. Sorry, just a second. So the percentage by number of atoms, that means how many number of atoms of hydrogen are there. But hydrogen, you know that it is so light element, so it is the lightest element. That is by mass it is only 73.4%. Okay, so that is why this difference is there. So if you count the total number of atoms in the sun and how many number is there for hydrogen and find the percentage, then it is 92. But if you find the mass, then it is only 73.4%, almost 75% we can take, or 73%, and helium is 25%. Then all the remaining comes as we say that it's just the dot. Okay, just a sample is there. And initially people thought that actually early belief was sun and stars share Earth's composition. Everything in the universe, it is the early belief that everything in the universe share the same composition as that of Earth. And Cecilia Payne, that is who you can see in this slide, she's a famous women astrophysicist, and she's the first one to get a PhD, first woman to get a PhD in America, in USA. So she's the first one to get the PhD in USA. First woman to get PhD. Okay, and she studied a lot about stars, and she used to work with spectrums, especially in Harvard University. She got a lot of spectrums are there. So spectrum, as you know, yesterday we discussed about those. So those spectrum from all the stars, there is a library of that, and Cecilia actually analyzed those spectrum, and then finally she found out how many or what is the composition of each stars and what is the fraction of them, something like how much hydrogen is there, helium is there. That is actually, so her discovery was actually a groundbreaking one, and her work revealed the composition is now dominated by hydrogen and helium. And anyway, it is not surprising right now, even though it was surprising at that time. Even if you take the case of Earth, it is not like that. Hydrogen is not the abundant element on the Earth's surface. But in the case of sun and other stars, and even if you take the case of the universe, it is almost similar. The hydrogen is the most abundant element in the universe, and helium is the second. Okay, so, and in the case of sun, the most elements exist as atoms with a few molecules. So why? So the sun, because of high temperature, when there is high temperature, the problem is that the molecules cannot exist like that. So molecules are actually made by bonding between atoms. Two or three atoms comes together and bond together to form molecules. But at high temperature, those bonds cannot exist, and they flew apart, and they exist as atoms. So that is why in sun most of them are existing as what is called the atoms. And another interesting thing, as you know, because of high temperature, again, no liquids or solids can exist due to sun's intense heat. Okay, so everything will be evaporated to gaseous state. Okay, and another interesting thing, many atoms are ionized. So I hope you know what is an ion is. That is, if you take an atom, the model that we discussed yesterday, it consists of nucleus and atoms around, oh sorry, the electrons around. So in the nucleus, if there is 5 positive charge or 5 protons are there, then there will be 5 electrons around them. Okay, so that usually on a normal atom or in a neutral atom, positive and negative charge of the protons are cancelled by the negative charge of electrons, so it is totally neutral. Okay, but when you take the case of a an atom in a star, something like in the sun, because of high temperature, again these electrons will acquire energy and it will leave the atom. Okay, it is not just jumping between the energy levels as we discussed yesterday. That is actually small steps, but here the atom will lose this electron, and once it loses the electron, you know that if it is removed an electron, now there is only 4 negative, okay, and 5 positive. That means there is an excess positive, and resultantly that atom gets a positive charge. Okay, so that we can make an atom positive by stripping one electron out of them. Okay, so in stars almost all the atoms are existing as ions. This positively charged or this charged atoms are generally called ions, and almost all the atoms, many of the atoms are actually existing as ions, and there is losing of electron, and that is why we can say that sun's environment is electrically charged. Okay, and it is not like the earth's atmosphere. Earth's atmosphere is not charged, but sun's atmosphere is charged because of the separate electrons, then separate ions and all, and this charged particles that is at high temperature together is called a plasma. Okay, and plasma is not just the case of sun, it is actually another state of matter. So in the case of states of matter, there are solid, a liquid and gas, and one more is there, that is plasma. So there are many, two or three more are there, two more are there, so you can just leave that. At least now this is the fourth state of matter, that is called plasma, which consists of electrically charged atoms, and electrons and protons are there. They are held, they are together, and it is called a plasma. The best example is actually when you see an electric arc or electric spark, if you remember, that is especially in the case of them, that Tesla coil and all, you might see some experiment with the electric spark. That bluish thing is actually the plasma. It consists of charged particles. Now let's discuss the structure and some of the prominent features of sun. Okay, so generally we can give a cut section like this, and all the energy that is in the sun is actually coming from the center. That is why it is given as some arrows, and you can see here this is following a path roughly like this. Okay, and it will okay, yeah, we will discuss that. Okay, anyway, the source of energy is not from the entire sun. The energy is being produced only at its center, at its core actually. Okay, now let us discuss each of them one by one, and the first thing we are going to discuss, you can see this layer of sun. Okay, that is called a photosphere. So photosphere means when you are observing the sun, okay, with your normal eye, that is the maximum limit up to which you can see. So you cannot see a star or especially sun inside the photosphere. Okay, you cannot pass through the photosphere. So it is like, so this is what you see when during a sunset or sunrise, or even at the daytime, what you are seeing is actually the photosphere. So here the layer of the sun becomes opaque. So but it is not usually when we talk about the size of the sun, what is the diameter of the sun, like that we are actually saying about the size of this photosphere. Okay, but actually if you go to the sun, okay, suppose you are traveling, even though it is not possible, even we cannot even go near the solar atmosphere like corona or even, but if you even go to, assume that you are going to what is called the photosphere, you cannot see this surface. Okay, you cannot see a solid surface like a cricket ball or anything, because it is gaseous or it is in a plasma state, and it is something like a fog. Okay, imagine there is a, or it is something like a sky. Okay, so in daytime you feel the sky as a bluish thing there. Okay, the color it's there, but anyway you can see something is there. It is a fixed roof is there for the earth. That is the feeling that we have, but we know that right now it is, there is no such a roof for earth, but we feel like that. Why? Because there are so many molecules, so many atoms are there in the atmosphere, and when the light scatters, okay, so light can penetrate through this atmosphere, but not up to a level. Beyond a level it cannot, so it will become opaque after a certain level, so that we feel it as an opaque roof or opaque fixed boundaries there. So it is something like when there is a fog is there, so even the fog is so thin, but when it is a whole lot of fog for a large distance is there, after a certain distance you cannot see. So this is also like that. So the atmosphere of the sun, it is actually so thin, but at the same time, when the light travels a lot through them, it is actually opaque. Okay, it becomes opaque. It is something like a fog. Okay, so this is the final boundary at which we can see, but above that photosphere, the remaining layer can be seen, but not normally. It is not normally seen, but what is the thing that we see normally? That is simply the photosphere. Okay, and the temperature of the photosphere is interestingly just 4000 to, it's not, it's obvious that some 4000 to 6500 Kelvin. Okay, so that is the range of the temperature of the photosphere. Okay, now let's take the next layer. Okay, so we are not going into the sun. Now we said about the photosphere, and we are going for the next outer layer. Okay, so it is something like this. I will show this picture. So we are not going into the sun, we are actually going out to the sun, outward. Okay, so this is photosphere. So the next layer, okay, that is called, okay, there is another layer that is, you can see this is marked here. This layer, okay, usually not seen with a normal telescope, or normal telescope in the sense, normal telescope with the proper filters. Never use a telescope to look at the sun without proper filters. Okay, hope you know that. Okay, anyway, so the chromosphere is not usually seen with a normal telescope. Even at a sunrise or sunset, you cannot see that. Okay, but this chromosphere, as the name suggests, you can see that it is next layer of sun, but there is a word chromo. Chromo means, usually in science, the term chromo is used when something is related to color. Okay, a colored thing, that is the meaning of chromo or chromosphere, or yeah, a colored surrounding. So why people called it initially chromosphere? Let's see. So chromosphere is initially found during a solar eclipse. When during a total solar eclipse, the main photosphere of the sun will be covered by moon. Okay, so at that time, the outer layers of the sun becomes visible. Okay, why it is not normally seen? Because when the sun is too bright, it is something like, imagine that there is a bright source of light. Okay, some bright torch light is there, and a firefly is sitting near to that. You cannot actually see that firefly. Okay, why? Because that bright light is there. Okay, so similarly, sun's photosphere is too bright, so that the nearby faint corona or the chromosphere cannot be seen. But during a solar eclipse, this chromosphere, this photosphere, the bright photosphere has been blocked by the moon, so that we can see the remaining part. Okay, so this is one natural way of seeing the chromosphere. At that time, using filters or by photographing method, we can take the photo of chromosphere. And there is, you can see this white thing, okay, like a crown, but before that, you can see this red color, okay, this red lining. So this red lining is actually the chromosphere. So don't imagine it as a circle, it is actually a sphere, and that is this sphere it is. Okay, and this sphere is around that, and we are only seeing one edge of that. Okay, so because of that color, it is called a chromosphere. And because since some color is there, actually scientists analyzed what it is, or again, it is some light. So they particularly focused that light through a telescope and fed it into the instrument that we learned yesterday, that is spectrometer, and analyzed this light. And they found that this red color is because of the emission lines of hydrogen. Okay, and its spectrum consists of bright emission lines caused by hydrogen. So why it is emission lines? Yeah, actually the chromosphere is actually at a high temperature of about 10,000 Kelvin. So when a gas or maybe hydrogen is there, that hydrogen is at high temperature. Okay, that means we are heating it. Okay, the sun itself is heating it up. So at high temperature, it can emit light. So that is the emission spectra that we explained yesterday. So that emission spectra is analyzed, and they found out that it is due to the hydrogen. So that is this chromosphere. Okay, and again this chromosphere spectrum, yesterday I mentioned, I think in 1868, observation of the chromospheric spectrum. Spectrum means the spectrum of chromosphere revealed a yellow emission line, okay, an yellow colored line that did not correspond to any previously known element. And that unknown element again then later found out to be helium. Okay, so that is another thing. Now another thing you have to notice here, what was the temperature of photosphere? Yeah, that is some 4000 to 6000. You take average some 5000 Kelvin. Okay, it is not proper average. Anyway, you take it as 5000. And now you can see the temperature of the chromosphere is double, even though it is an outer layer. Okay, see, the inner layer is cooler than the outer layer, or as you go out from the photosphere, the chromosphere is getting or the outer layer is getting more hot. Okay, we will see why it is so and later. Anyway, just note that. Okay, now the next interesting layer, which is the maybe the largest feature of the sun, that is the corona, and it extends millions of kilometers above the photosphere, and it also emitting light about half as much as light of the full moon. Okay, it emits light half of the light of the full moon. That means it is almost like a full moon day. But the problem is that that full moon is near to sun, so that we cannot see anything. That is a problem. But during a solar eclipse, you can see it like this ring. So this ring means it looks like a crown. Okay, that is why it is called. That is the name corona. The same naming convention for the coronavirus. Okay, but this is the first corona that we learned. Maybe you have, you might, for you all people, maybe the first corona is the coronavirus. Okay, so but nowadays there is no need to wait for the eclipse to happen to see the corona or chromosphere, because scientists can do, there are solar telescope out there in the space. Okay, and with that space, okay, there is an observatory called the Soho. Okay, you can go to its website and see the sun live. Okay, so what they do is that this is one such image. You can see, can you see this center ring? So this center white ring is the photosphere of the sun, and here you can see another disk. Actually, this is a disk which is actually blocking the sunlight, like that of the what is called, like the moon. So moon is a natural obstruction to sun during a solar eclipse only, and it is total solar eclipses are so rare. It is not that easy to find. It's there, but we have to travel a lot and all. But in this case, actually, we are blocking the sun with an artificial disk, and then the corona can be photographed. So that is the method. Now you see another interesting thing about the corona. Even though it is an atmosphere, it is a thin atmosphere. The outer layer of the sun, or outermost part of the sun's atmosphere, but its temperature is 3 million Kelvin. Okay, you see, even so much inside that, the temperature was just some 5000 Kelvin. Now it becomes 3 million Kelvin. So it is actually a puzzle for astronomy, the astrophysicists, and it still there are theories explaining why this is happening, or why this, but it's not yet a completely satisfied theory is not yet there. Anyway, some of the reasons are, and you just see this, take here, this is a photosphere, then chromosphere, this is the temperature, and then when it is reached corona, you can see that jump in temperature. So some thousands of at the peak it becomes a millions. You see that temperature rise. So corona and the photosphere, this much difference is there in its temperature. So the reasons are actually, one reason is that magnetic heating. Okay, so the sun's magnetic field lines tangle, twist, and reconnect. So I will explain why this is happening. So usually, if you take the case of Earth, okay, so Earth has, so you just take a bar magnet, okay, a magnet with the north and south, and if you map its field lines, or how that field is moving, or what is the direction of each magnetic field, if you find it out, you can draw some patterns like this, something like a spider, or okay. So this is something of a bar magnet. Similarly, if you plot the same for Earth, Earth also has similar thing, because Earth has a north and south pole, and you can map it like this. Okay, so this is, we know that, and this is happening because of inside the Earth there is something called the molten iron is there, and it is ionized. So when charged particles moves, there will be magnetic field. That is the same reason why the sun also have the magnetic field. But in the case of sun, there is a problem, because sun is not a solid thing. Okay, Okay, it is kind of a gaseous or gaseous or plasma thing. Okay, it is kind of a fluid. Okay, it can flow or move. It is not a rigid thing like a solid. Okay, so that is why this problem arises. That is why the magnetic field gets tangled and twist. So now, what is the problem of being a what is called as gaseous thing or a fluid thing? So because of, since it is a fluid thing, okay, the first problem is that, so it happens not just for sun, it happens for other gaseous planets like the Jupiter and Saturn as well. So since it is a gaseous thing, uh, when you take the case of Earth, so every place of the Earth, every part of the Earth, if you take, this is Earth, North Pole and South Pole, and this is the equator, and if you take a place at equator, it will complete one full circle, one full rotation, okay, self rotation, that rotation in 24 hours. And if you take a place here, it will also complete one rotation in 24 hours. Okay, every part on the Earth's surface make one full rotation in 24 hours. Okay, but in the case of a gaseous planet or in the case of sun, equator moves faster. Okay, equator moves faster, and as you go to the pole, it becomes slower and slower and slower. So just imagine, if you imagine something here, an object is here, assume that if there is a structure here, and this center part will move forward, so that what will happen, its shape becomes something like this, something like stretched. See, after some time it will become like this. Okay, and even after some time it will be so much elongated, something like this, so it gets stretched. Okay, so here the same thing happens for the magnetic field as well. Okay, so you can see this is one example of that. See, this is a normal thing, but now due to this rotation, so this rotation, that is different sun moves at a different speed, and or it takes different times to complete one circle, and that is called the differential rotation. So the different, this I will explain it later. It is explained in another slide as well, don't worry. So this is called differential rotation. So different part moves at different speed. Okay, so that is called the differential rotation. And due to differential rotation, you see this is elongating, and later it becomes toroidal. Its shape becomes entirely different. It was something like this, like the Earth's magnetic field. Now it becomes something like the wounded one. Even after that, this twisting will happen, and you can see they will tangle up, and this kind of this tangling up, and it is making some loops, twist and reconnection, etc. So, and that releases a vast amount of energy, and this events transfer energy to the corona. So this magnetic field lines twisting and tangling, etc., will cause to transfer energy to the corona, and that is heating. And another thing is that tiny frequent burst of magnetic energy. Okay, that means some kind of flares are we will explain flare later. Anyways, amount of energy, that is plasma, is actually uh, going out of the sun surface, so that it will reach the corona, and that the cumulative effect of that can generate significant heating. And another explanation is that thermal conduction suppression, that is, unlike typical heat conduction, the highly ionized plasma in the corona prevents efficient transfer of heat back to the cooler layer. So assume that the corona is heated by this magnetic heating. Okay, so corona is the outer surface. So now this corona is getting heated up. But when something is heated, what will happen? It will transfer it a temperature or the heat energy to nearby cooler layers. But the problem is that the nearby cooler layers, the photosphere and all, there is no good conduction methods, because it is so less dense, it cannot properly conduct the energy back to the cooler region. So these are some of the reasons supposed to be the reason why the corona is so high in temperature when compared with the photosphere. So despite this, there is the exact mechanism behind the coronal heating remains an active area of research in solar physics. Okay, still the answers are not satisfactory. So there are so many research is active. It is an active research area in solar physics. Okay, so now there is another thing called a solar wind. So sun's atmosphere produces a stream of charged particles, okay, and the charged particle, not that, and it consists of mainly protons and electrons. Okay, so it is not that heavy particles like maybe it is not atoms or anything. It is basically mostly protons and electrons, and this is coming out as a wind, okay, because of the energy. So, and this particle flow outward from the sun into the solar system at a speed of 400 kilometers per second. And an interesting thing is that it is 1 to 2 million tons of material is ejected from the sun every second. Okay, just see that amount, 1 to 2 million tons material each second through this field. Okay, and now the problem is that actually these solar winds are harmful for any planet, and that is but in the case of sun earth as well, it is a problem. And when there is heavy solar wind, which is called the solar storms, are there during those solar storms, back in some, I think 1980 or something, there is a famous event called the Carrington event. So when this charged particles comes, it can interact with the uh, earth's atmosphere or the earth's electrical grid systems and all, and it can cause so many damages. But it won't happen usually. Why? Because earth is not just a sphere like this, it does have a magnetic field. So magnetic field has an ability to deviate. So when some charged particles like solar wind is coming, it has the ability to deflect this solar wind particle, this charged particle. So that is what, so this magnetic field, the earth's magnetic field, is actually protecting us from the solar wind. But if it is a heavy solar wind or it is a heavy solar storm, it can actually affect our satellite systems, our electrical grid systems and all. And that is why scientists are closely watching the sun. So if you go to the Soho website and all, you can see that lively, you can see what is happening in the sun. So that live streaming that you can see, and from that we know that when there is a solar storm or something like that, and at that time the scientists, the people try to shut down the satellites. Maybe satellites will be rotated in or turned or tilted in a way that it doesn't get affected by the solar wind. So solar wind is actually affecting the space weather, and it is called the space weather. So this can affect the Earth's atmosphere or the maybe some satellites and all, and that is called the space weather. And there is another what is say an interesting thing that is happening because of the solar wind. That is when this particles comes, actually, even though you can see that this magnetic field lines are like this, it actually reaches the pole. So this charged particle can go through this magnetic field lines and reach the pole. When it reaches the pole, either the north pole or the south pole, it can interact with the atmosphere, that basically with the gases there, and so that it will emit some kind of those strike the molecules of air and causing them to glow, and they are called the auroras and northern lights and southern lights. Okay, so that is one reason. And another interesting thing, people actually initially discovered there is some flow is there from the sun, that is the solar wind is there. It is actually identified from comets. So comet has this long tail because the solar wind is actually coming in this direction. So all the particles or dust or maybe vapors and everything that is coming out of the comet because of the sun's heat is actually blown away in the direction. Okay, in this, if sun is here, it will be blown away in this direction. That is why the comet has a tail. Okay, so this is one reason. This is how we know that this initially we know, or this is how we discovered the solar wind is there. Now, another interesting phenomenon, which is even visible sometimes with the naked eye, if there is a giant sunspot is there, and you can see this is the solar disk. This is again the photosphere, and if you see the photosphere, you can see some dots. This is not any dust on the telescope or camera, but it is actually the dots. These dots are really the spots on the sun. Okay, and these spots are looking like this dot or black dot because it is lower in temperature. But when you hear it is lower in temperature, it is not that low. Okay, so something like if it is if you consider the remaining part, the other part of the sun, it is around some 5000 or 5800 Kelvin, 5000 Kelvin. And at the same time, this becomes some 3800. So that much only. So, but anyway, there is a temperature difference. So because of that lower temperature, when it is there, we feel that it's emitting less light when compared with the remaining. So that is why that relative feeling is actually causing it appears to be dark. Okay, so if it is possible to separate this, so just imagine that if it is possible to separate this uh, sunspot and keep it somewhere over here, then we will see it as a just a light emitting thing. We won't see it as a dark thing. Okay, so that is a sunspot, and sunspot is also causing because of that tangling of magnetic field due to the differential rotation. And as I mentioned earlier, the sun actually rotates. That initially actually found out by Galileo Galilei, not by using any other fancy instrument, just with his simple telescope. That is, he was able to track the movement of sunspot. So if the one sunspot is found here, after some days, the next day it is moved here, then moved here, then moved here. So if this should happen, that means the sun disk is actually rotating. So that is how Galileo actually estimated it is approximately 1 month. And now we know that near the equator, the rotation speed is 25 days. So in 25 days, the equator will complete one circle, but at the same time, in 28 days, it will take for somewhere here 40 degree. If you go to 80 degrees somewhere here, it will take 36 days to complete one rotation, and we call this behavior as the differential rotation. Okay, now the solar prominence, again, giant loop of magnetic fields or giant magnetic field lines. So you can see that the shape of this thing called the prominence, it is actually almost like a magnetic field loop, and this two spot may end at two sunspot as well. And when this is there, this giant loop of magnetic field, the plasma can actually enter into this magnetic field and it can make a giant loop. And you can see that it's not it is so giant in the sense that you can see its comparison with the Earth's size. Okay, so and the two edges of those prominence are actually anchored at the Earth's surface as well. Okay, uh, yes, and this is also consists of plasma, but it is not that hot like the corona. And there is one more thing similar to this, that is the flares. So solar flares are not this kind of, just a second, yeah, not like this stable thing, but solar flares are some ejection of materials. Maybe starts like this, but it will eject the material from the sun's surface and it will come to it will come to the solar system. Okay, so that is about the prominences. And now let's discuss about the heat transfer in a star. Okay, so basically to transfer heat, there are different methods are there. Okay, so heat transfer general methods are, one is conduction. So conduction happens, the best example is that when the handle of a metal spoon heats up as you stir a cup of hot coffee. Okay, so or if you place a metal rod on a candle or something, the other end, the holding end, get hotter and you will feel that heat later after some time. So why it is happening? Actually, that is called a conduction, because if you heat this side of a metal, then the heat will be transferred to this region and each atoms will transfer some energy to the next one, then to the next one, next to the, so they are all in contact, and by contact they are transferring energy. Okay, so they are actually transferring energy and finally it reaches here. So that is called conduction. So atoms or molecule pass on their energy by colliding with other nearby. Okay, so it is not moving. Okay, it makes some small vibrations. Okay, so that is why it is transferring. But anyway, when you take a spoon, the iron, maybe take as an iron rod, the iron atoms here is not moving to here, it is staying still there, but it is transferring heat. So why it is important, I will explain when we learn about convection. Okay, so Convection happens because of the current of, it is because of the currents of warm material. So the best example is that if you take some water and if you apply heat at the bottom, so here it is not happening by the conduction. So the water is already, it is a poor conductor, it won't transfer heat energy. So something like a water molecule here, it getting some heat, it transfer it to the next, and it transfer it. It is not like that. It doesn't conduct at all. What happens here? This layer of water molecules get energy, and it will go up. Okay, it will go up. So higher temperature will come at the top, and now the cooler one comes to the bottom. Then that cooler one gets the energy and it will go up, and it keeps on repeating like a circulation like this. Okay, and that is called the conduction. Sorry, convection. So that is called the convection. This is how the atmosphere is heating up. This is how the water is heating up. Okay, so that is convection method. And now there is another thing, that is radiation. That is kind of a direct transfer. So imagine that there is some so bright light is here, or some hot body like the thermal heater, electric heater is there with some red hot coil. Now if you stand here, you can feel that temperature. It is not, even if there is no wind or anything, you feel that temperature that is coming directly to you. That direct transfer of photons or that light to your body or wherever it is intended to be, and that direct transfer of photons is called the radiation. So in the case of stars, the conduction won't happen, because for conduction to happen, it should be something like a solid thing, or the molecules of that, or the material atoms of that thing should be so close by sitting together. Okay, that is one reason why it can conduct. But in the case of sun and all, the material is not that close, or it is not that dense, so the conduction won't be possible in the case of the sun, and generally in the case of stars there won't be any conduction at all. Then other two things that is happening, that is the radiation and convection. So initially the energy is formed at the core, and that energy is transferred as radiation. And there is another interesting thing, that is this radiation is not directly coming to the surface. Okay, so suppose that some energy is coming from the reaction that is happening, so that energy get absorbed by another atom or some ion there. It will get that energy, absorb that energy, then it will re-emit that energy. It will again re-emit, another molecule will absorb that and it will re-emit, it will re-emit. So when, if it, even if it starts at the core, the light will take a long time moving like this, like this, like this, like this. I don't remember the exact time taken for that. Anyway, it will take a long time, I think some years to reach the surface, at least to here. So once it is reached at this layer, and so that here all these things, it is the radiation happening, but it is not like this picture shows. It is not a direct transfer. It takes a lot time to reach here. And once it is reached the convective zone, then convection is happening, and that is how the heat is transferred to the photosphere or the outer layers, and that is emitting from here onwards. The light is coming to the earth as radiation. Okay, again actually it is radiation, but inside the sun when we discuss, we can say that this is radiation then convection. So this zone is called the convection zone, and this is called the radiative zone. Okay, so that's it. In stars which are much more transparent, so transparent means in the sense it is not that dense. Okay, uh, radiation and convection are important, whereas conduction can usually be ignored, or it is almost zero. Now let's discuss some interesting mathematics. Okay, just a second before going into that. Uh, so the question is that what is the source of this energy? Okay, so what can be caused this much energy? So yesterday we learned that there is something called the solar luminosity here. That means the energy emitted by sun, how much it was. We actually uh, you have seen that how much it was there. Okay, so that we that is called the solar luminosity. It is of the order of 10 to the power 26 per second. So 26 joule per second. So how we get this much amount of energy, that's the question. So what is the source of the sunshine? Okay, that is what we are going to answer. So as a common example, or what we know, something that generate heat and light, that one thing we know, that it's the burning of some coal or burning of some fuel. So when it burns, it gets heat out of that. So that we know. So people initially thought that it may be because of some burning. So every burning is actually a chemical reaction. So fuel burning is actually called a chemical reaction. So people assume that it may be due to some chemical reaction, and due to that chemical reaction, sun emits an energy that is approximately 3.8 into 10 to the power 26 watts, or 10 to the power 26 joule every second. Okay, so then people try to calculate how much energy will be there, or if the chemical reaction is happening, if some gasoline is burning or some fuel is burning in the core of the sun, then let's see how long the sun can survive with that energy. So for that, they have done some calculation, interesting calculation. You can see, so the burning of hydrocarbons or hydrogen, any kind of burning, it is usually the chemical reaction. So and 10 raised to 7 joules is emitted per kilogram. That means if you burn 1 kilogram hydrogen or hydrocarbon, something like the coal or maybe petrol or diesel or anything, so approximately we get 10 raised to 7 joule if you burn 1 kilogram. Okay, now just imagine that, let's assume that the entire mass of the sun, so entire mass of the sun is 1.989 into 10 to the power 30 kilogram, okay, is available for the chemical burning. So this entire mass is getting burned. Assume that it is like this. And now let's find out how much energy that we can generate from this. Okay, how much energy that we can generate. Okay, so this much kilogram means total chemical energy that is from the sun. Okay, so every kilogram will give you 10 raised to 7 joule. How many kilograms are there? 1.98 into, okay, that is simply 2 into 10 to the power 30. That much kilogram is there, and each kilogram will give you 10 raised to 7. Okay, that means 2 into 10 raised to 37 joules of energy we can get from the entire mass. Anyway, we are taking a huge what to say an assumption, that is we are assuming that the entire mass is being converted into energy. So just leave it, our entire mass is available for burning. Okay, so anyway, even with that assumption, we get it as 2 into 10 raised to 37 joule entirely. And now we know that every second already 10 raised to 26 or 3.8 into 10 raised to 26 joule is being emitted. Okay, so total energy available is 2 into 10 raised to 37, and let's take this 3.8 to be 4. Okay, I am simplifying it for calculation. Okay, so divide it with the 4 into 10 to the power 26. That means this is the total energy that is available, and each second this much energy should come out of this. So we can cancel it. So I get a 2, that means 0.5 into, this means 10 to the power 11, or 5 into 10 raised to 10. Okay, I will give you the proper calculation there. So this much seconds the sun can burn, that is 5 into 10 raised to 10 seconds the sun can burn with a chemical reaction. So 10 raised to 10 seconds, you may feel it like a long time, but if you calculate it properly, you can see that, so time is 3.8, that is 5.2 into 10 raised to 10 second, that is almost, we got the correct answer, 5 into 10 raised to 10, and you get only 1660 years. Already we know that the calendar itself, the Julian calendar itself, as Gregorian calendar itself, already more than 2000 years old. So we know that this is not the case, because even if the entire sun is born, it can only last for some less than 2000 years. So this is impossible. So with this chemical reaction, the sun cannot survive. Why? Because we already know that everything, the earth is so much aged than that. And there are some methods to find out the age of the rocks in the earth, and by analyzing the age of those rocks, the age of those rocks are something around 4 billion years. Okay, so rocks on the earth are 4 billion years, means the sun should at least burning for 4 billion years. Okay, and based on that, we know that by this calculation, we are only, the sun's lifetime is something around 1500 years. Okay, so it is not even comparable. So the chemical energy is not the reason behind the reaction, or is not the source of energy in sun. Okay, now let's think that instead of that, there is another kind of energy called a gravitational contraction, or energy from gravitational contraction. That means if you have a heavy thing and the gravity is pulling it inward, okay, and when it is pulling it inward, obviously it will contract. So as we compress something, it gets heated up. It gets higher and higher temperature. And here, who is doing that thing? It is gravity. So from that gravitational energy, does this happen? So that is the next question. And they calculated it. So the gravitational energy, the equation is gm square by r, where g is the gravitational constant and m is the mass of the sun and r is the radius of the sun. And if you substitute all these things, you get it as 2.3 into 10 raised to 41 joules. Okay, but you can see that it is much higher than that of the 10 raised to 37 joule that we got from the chemical reaction. It is 10 to the power 41 joules. Okay, now is this enough for burning for billion years? Yeah, again, divide it with the luminosity, divide it with the luminosity, so you get 10 raised to 14 second, so it is 20 million years. Again, it is just million years only. So again, the source of the sunshine is not what is called the gravitational contraction. It should be something else. Now, what is that something else? So the answer for that comes from this famous scientist. I'm not going to mention his name, and this famous equation that is the popular, the world's most popular equation, that is E equal to mc square. Okay, let's see before that what are the terms in this equation. So E means simply usual meaning, that is energy, and m means mass, and c means speed of light. Okay, so energy, mass, speed of light, you got it. Okay, now let's see, that means here mass, you can take it as something like the mass can be converted into energy. Okay, so what mass, where it comes, let's discuss later. Anyway, this meaning of this equation is that the mass can be converted into energy. So another way we can say that energy is mass is a condensed form of energy, something like, or they are interconvertible. Okay, so mass can be converted to energy, energy can become matter as well. Both kind of reactions are actually happening in science, in physics, so no problem. So this is the basic idea of that equation. Now let's see, let's go to something else. We know that there is an atom, and atom has something called a nucleus, and in the case of that, if this is, we are not in this case we are not going to discuss about the electrons. Okay, we only need something called a nucleus. Now we are going to discuss about the maths, or the science of nucleus, or physics of nucleus. Usually that branch of physics is called the nuclear physics. Okay, and if it comes to astrophysics, which is also called, there is a branch called the nuclear astrophysics as well. Okay, now let's go. Now if you take that, just think that this is 3 proton and 3 neutrons together forms the nucleus. So if you take it separately, that is 1, 2, 3 protons and 3 neutrons separately, and find the total mass of them. Suppose using a weighing balance, you are measuring its weight, you get a number. Assume that some 7 you got, or 6.5 you got. Okay, just a number I am giving. Now you are weighing the same nucleus, which is actually made up of the same thing. Okay, this is made up of the same material, and if you measure the weight of that, it should also weigh 6.5. Okay, that is the basic notion of mathematics. If you take 10 balls and each of them weigh 1 kilogram, the total mass is 10 kilogram. then even if you club it together or take it together, then its mass should be again 10 kilogram. There shouldn't be any loss at all. But in the case of nucleus, it won't be 6.5. This mathematics won't happen in the case of nucleus. The mass of that nucleus will be less than that, maybe 6. So there will be a missing of 0.5. Okay, some 0.5 unit of mass has been missing from there. So what happened to that missing mass? So that missing mass is actually used to form the nucleus, because to hold all this nucleus together, or all these balls like the protons and neutrons together, it needs some energy, and that energy is called the binding energy. Okay, now that where the nucleus get that energy, that is from this missing 0.5. I'm just giving this rough numbers just to make the calculation simple. Otherwise, I will give you the actual numbers later. That is something like 1.000 something. It's not that easy to convey the idea, but this is just to convey the idea. I am giving this blunt numbers or random numbers like this. Okay, so this is 0.5. So that 0.5 unit of mass is converted into its binding energy, or that energy is used to hold the particles together. Okay, so and how it becomes energy? This is a missing mass. That mass can be converted into energy using this equation, A is equal to mc square. So this is one way, or one case in which some mass is missing, and that mass becoming energy. Okay, now let us take another example, and now you got that difference. So I will show you that in a graph here. So for example, you have a carbon nucleus which consists of 6 proton and 6 neutron, and if you take it separately, it weigh more than that of the carbon nucleus. So nucleus is smaller in mass, separated nucleons. So nucleons means what are inside the nucleus, or protons and neutrons together called nucleons. So separated nucleons has greater mass. So that means there is a difference in mass which is used for binding these particles together. Okay, now there is another case. Suppose if you are taking 4 protons, okay, so I will give you the detailed reaction later. Suppose we have 4 protons, or 4 proton means hydrogen nucleus. So hydrogen has a single proton at the center. That means we can call it as the hydrogen nucleus. A proton can be called as the hydrogen nucleus as well. Now we are adding them together. So each of them has a mass of 1.007825. It is not kilogram. I have put here U. U means that is a unit of mass which is used in measuring the mass of atoms, maybe protons, like that. So that is called the atomic mass unit. This can be converted into kilogram. Okay, so sometimes it is written as AMU or U. That is enough. Okay, so now this is that much atomic mass unit is there. So this is why I am using that this exaggerated numbers, because using this 00 is not that appealing to explain this. Okay, now let's add them together. Yeah, the total is 4.0313 atomic mass unit. You can try adding this, no problem. Anyway, I have calculated it. Now let's take these 4 protons, or the hydrogen nucleus, can be combined together through some reactions. We will explain those reactions later, and those reactions are not the chemical reaction, they are the reactions between the nuclei. Okay, so between the nuclei. Okay, if you take different nuclei, they are actually reacting together. That means that reaction is called the nuclear reaction. It is not chemical reaction, it is the reaction of nuclei. So it is called a nuclear reaction. And by some series of nuclear reaction, I can convert or take this 4 of them together and make a helium nucleus. Okay, but along with some other things anyway, but it is negligible. But roughly we can say that we are taking 4 hydrogen nuclei and making a helium. And now let's check what is the mass of that helium. If you calculate the helium mass, you will get 4.002603 U. Okay, so see what is it is this helium So you may think that one proton comes here, one proton comes here. What happened to where does this two neutrons comes? Actually, there are way to convert the protons to neutrons during a this kind of reaction, during a nuclear reaction. So don't worry about that. I will give you the detailed equations later. This is just for the reference, or just to understand what is the defect or what is the difference in mass and all. So here you see this is 4.0313, which is higher than 4.00263. So what is the difference? So if you find the difference between these two, there is a deficiency of 0.0287 unit in the case of helium. So this is the missing mass, or we call it as the mass defect. Now this mass defect has to be converted into energy. Okay, or it becomes the energy. So that is the energy output of this reaction. Okay, so let us calculate that. So 1 unit of this is actually 1.66 into 10 to the power 27 kilogram. So 1 atomic mass unit means it is this much kilogram. It is so tiny number, you see, 10 to the power minus 27. Now delta M is equal to, you can calculate this into 1.66 into 10 raised to minus 27. We are converting it into kilogram. So we get 4.76 into 10 raised to minus 29 kilogram. Now we can insert this delta M into E is equal to mc square equation. So finally we get, while converting 4 hydrogen nuclei into helium, you get an energy of 4.28 into 10 raised to minus 12 joules only. It is so tiny value, just see, it is not a big number. Okay, but this is the energy from one reaction. Okay, now we got it. Now is this enough for burning the star for a billion years, or maybe 5 or 10 billion years? Let's see that again we can calculate. So the mass converted into energy, the energy released is about 4.3 into 10 to the power minus 12. This is the energy released for one such a reaction. Okay, for hydrogen is converted to helium. Now let's do that calculation. Let's see, I'm not going through this calculation. Now total mass of hydrogen in the sun. So approximately 75% of the sun's mass is hydrogen. Okay, so how much hydrogen is there? That is 0.75 into 1 point. This is the total mass of the sun. Its 0.75 is hydrogen. So we got it as 1.49 into 10 raised to 30 kilogram hydrogen is available for the reaction. Okay, so 8 hydrogen atom has a mass of about 1.67 into 10 to the power 27 kilogram. So how many hydrogen are available? So the total hydrogen weighs this much and one hydrogen weighs this much. So if you divide it, this much number of hydrogen atoms are available in the sun for that reaction. Okay, now each hydrogen will give you, okay, each fusion consumes 4 protons. So you have to divide it 4 proton. So this means 2.23 into 10 raised to 26 fusion reaction, and energy released per reaction is this much. So 2.23 into 10 raised to 56 into 4.3 into 10 raised to minus 12. Just leave this calculation, you can refer it later, don't worry. Anyway, we get a number, the total energy expected from, okay, this nuclear reaction of hydrogen is 9.6 into 10 raised to 44. Approximately, if you take it as 10 raised to 45 joules. Now let's calculate, oh sorry, I haven't included that calculation, sorry. Now we can calculate how long the sun can burn. So this is the total energy, 10 to the power 45 joules. And what was the solar constant? Solar constant was 10 to the power 26. I'm just taking the powers only, so 10 to the power 26. So that means 10, if it is 25, it is 20, yeah, 10 to the power 24 second. The sun can burn up to 10 to the power 24 second. Now we can convert this 10 to the power 26 second into what is called years. Okay, so simply let's find out what is 1 year in second. 1 year in seconds. Yeah, 3.15 into 10 raised to 7. So just take it as 10 raised to 7. You might think that why I am doing this, always neglecting this number and all. I will tell you later. So 10 raised to 24 by 10 raised to 7 means this is 17, 10 raised to 17 years. Okay, that means how many billions are there? So 10 raised to 9 into 10 raised to 8. So it will burn for 10 raised to 8 billion years. Okay, this is way more than enough. Okay, so this calculation is not that accurate in the sense that we are considering that entire hydrogen is available for reaction and all. That is why we got of the order of billion. And why I am neglecting this 8.92 is taken to be 10, and sometimes that 1.67 is being neglected. Why is that? So when you calculate this huge number, something like the 10 raised to 24, multiplied it with the 3 is not that big. Okay, so we need only the order in which how many billions are there. So that much calculation is only necessary to get a rough estimate, okay, or to get whether it works or not. Okay, so this is actually astrophysicists usually do, put all the rough numbers and let's find out whether it works or not. And if it works properly, then we can actually do the proper calculations. That's not a problem. Okay, so this is just for the rough estimate. You can do it properly with proper numbers and all later. Okay, so that is the source of sunshine. So finally, we came to the conclusion that a reaction like this, okay, so that entire reaction that I mentioned roughly like the hydrogen nucleus becomes helium, that actual reaction is something like this. First, it happens through a series of steps, at least 3 steps. This is called the proton-proton chain or PP chain. This particular series is called. First of all, 2 protons. So hydrogen nucleus means 2 protons comes together and form this thing, that is H2, that is 1 proton and 1 neutron. Okay, and along with that some particles like neutrino and positrons are emitted. Okay, you can that is so negligibly small, the mass of neutron and positron is it's an electron, it's like an electron with a positive charge. Okay, now it is created here. Then now such an H2 or this is actually called the deuterium. Okay, the isotope of hydrogen. So or the name of this is deuterium. So then that deuterium nucleus combined with an hydrogen nuclei, then forms some in each step there is energy coming and it becomes a helium 3 actually. So that helium 3 again works with another helium 3 and finally we get this one. Okay, so in all these steps there are so many. So finally if you sum up that reaction you will get something like 4 hydrogen are taking part and finally we are getting a helium 4. So hydrogen nucleus is being converted into helium nucleus along with some energy. So this is the cause of energy, or this is the energy source of stars.